Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Dr. Gianluca Iaccarino, who is the director of the Institute for Computational Mathematical Engineering and a professor in the Mechanical Engineering Department at Stanford University. He received his PhD in Italy from the Politecnico di Bari before joining the faculty at Stanford in 2007. Since 2014, he is the director of the PSAP Center at Stanford, funded by the US Department of Energy, focused on multi-physics simulation, uncertainty quantification, and exascale computing. He received the Presidential Early Career Award for Scientists and Engineers Award, and he is a fellow of APS. Today, Gianluca will talk about autoencoders for aerodynamic predictions, which is an exciting topic. So please expect a wonderful talk from him. Now, let me ask a question to Gianluca, if that is okay with you. Is it okay? Asking you one question?
Absolutely.
Okay.
Yes.
Okay. In audience, there are many students and early career researchers to this DDPS seminar who are currently working on computational and data science. If you give them some sort of career advice, what kind of advice would you provide?
That's a great question as a start. I'll say something that I tell most of the students that pass through ICME and through Stanford, which is everything that you do in research should be driven by curiosity. You should be really have open mind in terms of asking questions, and I think that should be a real passion in the sense that should be a natural tendency to sort of be curious and try to get to the bottom of what is that you're seeing, why it's happening, and that curiosity can really drive you to get sort of a learning in terms of the work that you're doing that can be really very, very powerful. So curiosity as a main driver in what we do in research is critical.
Absolutely. Thank you. Thank you so much for the wonderful answer. Okay, the stage is yours.
Thank you very much. Thank you for the invitation, and thank you for joining. As I mentioned, as was mentioned, I'm going to talk about autoencoders. I wasn't sure about, again, the composition of the audience, so this talk is going to be relatively high level to give you some of the basic ideas of the work that we have been doing, and I'm happy to discuss this in more details either during the Q&A or maybe afterwards. You can feel free to reach me if you have questions. So the first thing I want to say is that my presentation is going to be a little bit different than what I typically do in my daily work. As was mentioned, I'm the director of the PSAP Center at Stanford, and this is actually a slide that represents the work that we're doing in that center. It has to do with laser-induced ignition of rocket engines. You're seeing a still visualization and then animation of the combustion process, and we're working on exascale computing platforms to do these simulations at scale. There is a component of this project that has to do with machine learning and uncertainty quantification that's obviously connect to the presentation today, but I'm not going to really give you any details of this work. If you're interested, again, I would be very happy to discuss it afterwards. And so instead today, what I want to tell you is really a story about a project that I started when I was in sabbatical a couple of years ago, now 3 years ago, and started really as a curiosity, try to learn more about some of these algorithms that we all hear a lot about. And the project revolves around aerodynamics, which is sort of the work I was doing at the time, and a specific class of algorithms that many of you might be familiar with. But to sort of introduce them, I'll sort of use a very, very sort of simple simple connection to tools that instead we use perhaps every day in our life. You know, the simplest approach that you can think of in this realm is gzip. Gzip is, as you're familiar with, is a compression tool, allows you to take a big file and reduce its size. And it's a relatively straightforward and a relatively innocent tool. It's actually very sophisticated, very effective. And it's what's called the lossless direct compression. So allows you to go one way, meaning from the original file to the compressed file, but also come back with the exact reconstruction of the original file, okay, if you want to uncompress it or unzip it. Now, this is, as I said, a tool that we're all familiar with. Perhaps another tool that is, again, in the same spirit, so a compression tool, but that many of you might be familiar with from perhaps application, is the singular value decomposition. A singular value decomposition is, again, typical similar compression tool where you start from an object, in this case, an image. It can be a different, it might not be necessarily an image, but perhaps a matrix or just a file. And the idea is that you take this image and you compress it, reduce its size by performing a matrix decomposition in terms of linear algebra. And this matrix decomposition leads you to a reduced representation, in this case, that has an effective size that is about 1/10 of it. And the advantage with respect to the previous tool is that it has a tunable parameter, which is the number of singular value that you preserve. This is the amount of compression that you force in the algorithm. And as you reduce that number, in this case, it's 30 singular values. If you reduce it to 6 or even lower, to 1, obviously you obtain a much more compressed representation, but obviously also you lose information. You're not representing that original object in the same way. But again, you achieve a very high level of compression. Now, the problem with this is that this is a compression that is lossy, in the sense that you're losing information and doesn't allow you to go back to the original version of the image. But it is a very powerful method. It's actually used in almost every algorithm that has to do with large data set, at least in a linear sense. And it provides you what can be referred to as a latent representation. The singular value are sort of a new representation of the original data that has captured some of the features, some of the character of the original image. Now, what I want to talk about today is actually a version of this process, which is based on machine learning, which is the basis of an autoencoder. An autoencoder is a compression algorithm, very similar to what I described before, but it's a much more powerful because of the generality of the representation that it uses. Allows you to take, again, now not just one image, but perhaps a large number of images. In this case, MNIST is a classical database, a classical test set for machine learning that includes 70,000 images. So a very large amount of data, in this case. Equivalent pixel is sort of a representation of how much data we have, and allows you to actually compress it in a very reduced form and regenerate some of the images, or perhaps generate a large set of images based on, again, a representation in terms of feature that is very, very compressed. In this case, with only 2 latent variables, we are able to actually reproduce the entire data set in a sort of a relatively effective and accurate way. Again, it's similar to before. It's a lossy compression. It cannot really reconstruct exactly the original images, but it is very powerful and is based on a representation that uses nonlinearity as opposed to SVT that instead only uses linear operations. So what I want to talk to you today is really autoencoders applied to aerodynamics. Again, I don't know how much you're familiar with aerodynamics, but this is a typical application of in the aerodynamic context. This is flow over a full aeronautic configuration, a typical test case in aerodynamic analysis. And today we can do these simulations fairly effectively and accurately. So we can actually reproduce, for example, the lift characteristics of a full airplane very accurately, all the way from low angle of attack to high angle of attack, which is the angle, the incidence that the airplane has with the incoming flow. And the prediction in this case can be run on a large-scale system, in this case Summit, about 100 GPUs, with a relatively small wall clock time, so with good turnaround. Now, unfortunately, although this is the state of the art, and we are we can predict very accurately what happens in the physics, the problem is that we are still limited in the number of calculations we can do, for example, for design. And so the idea is to try to use knowledge and these methods like autoencoders and other compression strategy to build databases of these calculations and then perhaps generate new cases that have not been directly simulated through high fidelity simulation. So that's sort of the reason why we started this project, to try to build tools that allow you to take some of these data sets and compress it and allow you to generate additional data, additional information. So just to summarize sort of what we typically do in aerodynamic simulation, in all physics simulations, this is sort of the process. We start from basic principles. We build a conceptual model, which is a set of PDEs typically. We cannot really obtain solutions directly, and so we go through a discretization and a computational algorithm to actually find an approximate solution, and we use supercomputers to solve the corresponding numerical computational problem that emerges from that algorithm. And that allows us to actually compute the quantity of interest and the solution we care about. And the point I want to make here is that this is a typical deduction process that we follow from theory to actual data. So the framework is generic, is general, and the example that we obtain is actually one specific instance of the solution. Now, the other thing I want to, and then I'll stop in terms of the physics of the problem, at least in general, is that I'm going to show you results for two different scenarios. The first is when we actually operate an airfoil in this case, or you can think of it as a wing of the airplane, in a steady fashion. As we change the angle of attack, we obtain a curve, which is the blue one here, which sort of represents the fact that for low angle of attack, the behavior is basically linear. The lift increases with the angle of attack in a linear fashion. And then it reaches a limit, which is a stall, where the phenomenon becomes nonlinear and the lift starts decreasing. Now, a different story, which I also use to illustrate the results here, is what happens when you have an unsteady motion. So the airfoil goes to a periodic motion of changing in angle of attack. But you see that the behavior in this case is the black curve here, is similar in the sense that you have a linear increase of the lift, and then eventually the lift drops, and you have this sort of unsteady behavior that then turns back into the low angle of attack as you sort of oscillate between positive and negative angle of attack. So I'm going to show you these two regimes because both the steady and unsteady results to illustrate the power of some of the methodology that I'll describe afterwards. So let's talk about machine learning now. In a general setting, compared to what I shared to you before, the approach is very different in this case. We don't start from first principles, from physical understanding and conceptual model. We actually start from data, from examples. We build a statistical representation of that data that can be very sophisticated or, in a sense, relatively simple. Then we train the model. In this case, we actually compute the parameters corresponding to that statistical model. And then we are able to, for example, recognize, classify the images that we get, so the data, the examples we get, or perhaps produce new examples. To trivialize these, the simplest example of data-driven model is regression. In a regression setting, we assume a function that represents the data, at least that we believe represents the data, in this case a quadratic function. And the objective of the algorithm is to find the coefficients, A0, A1, A2, that approximate or minimize the approximation error with respect to the data, of this model with respect to the data. Once we have completed that process, which obviously is the training phase in a machine learning parlance, then we have a method, an approach that allows us to generate new data, meaning that with the new x, we can compute a new f of x, which represents now new data that is unseen, that has not been part of the training. So this is the simplest model. Obviously, the models we typically deal with, and in particular, the models that I'll talk about, have millions of parameters, order 10 million parameters. They're much more complicated than a quadratic function. They're still not linear, but obviously have much more complexity embedded in it. But in principle, they have the same spirit in the sense that you start from initial guesses of this parameter, then use the data to actually learn what the best fit and the best parameters will be. From the process that I described, this is actually an induction process. So we go from data to an actual theory, in quote. Obviously, it's not a theory per se, but gives you sort of the sense that we don't start from assuming knowledge of the problem necessarily. We start from example and we try to build a knowledge a posteriori. And so to illustrate this, the simplest example that we started from was a database of flow geometries. This is an example that you see in literature these days. There have been many similar sort of applications. In this case, the geometries are very simple. They're bluff bodies, just two-dimensional bluff bodies. And these are represented in the first columns here, the first and third columns. They're basically just a representation of the geometry. And the second column is actually the velocity distribution. So red implies low velocity, the wake, and then the flow around this geometry is captured through velocity magnitude. Now, if you pass these images, very much like we passed the digits in the original example, we can actually then build a representation where we can accurately predict what happens around new cases, geometries that have not been part of the database. And everything looks reasonable in this case. You can actually show that the true solution actually is close to the predicted solution. You can quantify the errors and so on and so forth. And it seems like everything seems to be pretty trivial. Now, again, talking about the answer I gave before, curiosity, right? This seems to be all done. Well, the first thing we tried is to push the algorithm and see what happens if you do something a little bit different that perhaps was not anticipated when you built this. And the simplest thing I could think of is what happens if you have multiple bodies. So rather than one, now I give the autoencoder more geometries. So in this case, again, the training was done before with single bodies, and I'm asking the autoencoder to extract a new data set now on a geometry that is completely different, completely outside of the scope. Now, if you look at the results here, and that was the part that was interesting to us, it's very difficult to, now obviously, this is the prediction, so you might argue we don't know if it's accurate or not. We could compute the true solution, but just looking at it, you actually cannot tell if this solution is right or wrong. It's very reasonable. It's, seems to be capturing the fact that there is some interaction between these objects. Again, it's not something that was coded already in the training set, but it seems to be reasonable. And actually looking at the true solution, there is clearly some discrepancies, but they are not, completely off, right? So the interesting thing here is that the idea is we wanted to perhaps break the algorithm, and at first glance, it's difficult to guess if the algorithm was actually broken or not. And so this sort of stimulated the question of how can we build confidence in these algorithms so that the results that we obtain are actually results that we can interpret even in the absence of the true output, right? In some cases, we don't want to need to compute the output every time we want to check the solution. So how can we build automatically confidence in the prediction of these methods? And so this is how the entire project started, and how we sort of trying to go to a method where we build a process in the construction of this autoencoder that allows us to really interpret the results of the process in a way that is informing the confidence we have in the output. So just to sort of summarize what the autoencoder is, as I mentioned, is a compression technique. The basic idea is that you are trying to build an algorithm that reproduces the input. So the input and the output are basically the same information, and you're going through a bottleneck. You're basically compressing the information to a smallest possible set, which is sort of this red bottleneck in the middle, which is sort of called in the machine learning parlance the latent space, the latent vector. And the user controls the compression size, right? So like in the SVD, you control how many singular value you retain to represent the rank of the problem. In this case, you keep a certain size for this latent vector. The way we construct the autoencoder is that we include both convolutional layers and fully connected layers. The reason is because physically we expect the input to be aerodynamic flow fields. So we want to make sure that there is invariance that is embedded into the network, and also coupling between information in the data that we are providing. And so we kept both a set of convolutional layers and a set of coupling layers. And there are obviously many variants in the literature of the autoencoders. I'll tell you a little bit of the flavor that we are using, but we have done extensive comparisons also to other type of autoencoders that I won't discuss here, but I'm happy to, again, discuss it in more details. So specifically, in the way we built this framework, we wanted to be very principled in the way we actually approach the problem. And so there are effectively 4 steps. The first step is the construction of the database. And the second is the actual training, so the machine learning training of this network. The third is what we call latent space conditioning, and is a way to map the database inputs to the latent vector that is done after the training. So this is a step that does not affect the training itself. And then finally, once you have completed this, you have now a methodology that allows you to do predictions, meaning that you can generate new geometries or new problems and create solutions out of that. And typically, this only involves the decoder, so the second part of the network that we have constructed. So just to give you a little bit more details of exactly what we are talking about, the first step is to actually the construction of the database. What we have done in these problems is to build databases of airfoil geometries at different geometries, different airfoil thickness for different angle of attack. And typically, we limit the number of cases quite substantially. So we typically have an order of 30 or so cases to do the entire process. So we're not talking about extensive data sets. And the reason is because eventually we want to move towards very high fidelity data sets. And so we are expecting that order of 100 is really the limit of what you can generate, both in terms of computational costs, but also in terms of storage. There are some details of how the actual data sets are transferred to the machine learning tool. So basically, how we organize the database, that I can talk more about it at the end. But in general, we do need to build a representation that is amenable to a machine learning tool. So we have to summarize these data sets into basically a single vector, or basically a single tensor that captures the solution in space, but also in terms of different variables, for example, density, momentum, temperature, and so on. Now, the training itself is, I mentioned already, is an autoencoder. We typically, because of the limited data set that we use, limited size of data set, we have also a relatively small number of parameters, order 10 millions. And a very, very small latent dimension. This has been our goal, to sort of make sure that the latent space is as small as possible. For example, this is a loss function for our problem, for this problem that I'm mentioning here, at different values of the latent space, different sizes of latent space. So as you can see, for p equal 1 and p equal 2, effectively, the loss function stalls, does not really decrease anymore after about 500 epochs. Whereas as you increase the latent size, the loss function reduces a little bit more, although effectively after 3, 4, and 5, at 3, 4, and 5, effectively reach the same level of convergence. And effectively, the autoencoders perform in the same way, meaning that a latent size of 3, for example, 2 or 3 is sufficient actually to summarize and compress the information that we are giving the reactivity autoencoder, at least with a fixed architecture. Now, let me say a few words about the mapping, the latent space conditioning. So the basic idea is that the autoencoder only has access to the flow fields, the entire solution, but doesn't know anything about how that solution has been generated. What are the inputs for that particular data set that we're considering? And so what we are doing in this case is that we are actually building a mapping between the true inputs. So for example, the angle of attack and the latent dimension, the latent vectors, the latent quantities. So this is a typical example of this mapping where we have an autoencoder of size 3, so 3 latent variables. And what we do is that we map the 2 inputs of the database, in this case, the thickness and the angle of attack. These are all the solutions that we generate to build the database onto the latent variables. And this allows us then to go from the input variable to the latent variables, and then eventually through the decoder to the actual solution, synthetic solution, or the reconstructed solutions. And so just to complete then, once you have this conditioning or this mapping between the input and the latent variables, then you can really generate new solutions. And because you can extract, for example, a new airfoil at a given thickness for all the angle of attack, and then you can build an actual solution. And this is an example of this case, of this dynamic stall case, where the airfoil is oscillating at different angle of attack. And this shows the comparison of the Mach number, one of the quantity of interest, comparing the actual solution, the CFD will be the true solution, that again is not used in this case, and the synthetic solution, which is the result of the autoencoder. Now, in this particular case, the NACA 0012 was in the training dataset, so this is one of the cases that has been seen by the autoencoder. But you can do the same thing with a case that has not been seen. So this is the NACA 0020 is beyond sort of the scope of the database or the training set. And the results, again, are reasonable. So what you're seeing, again, is the comparison of the synthetic and the true solution. Now, we can argue if the results are actually as accurate as possible and so on. But remember that my goal here was not necessarily to get the best possible autoencoder, but to try to understand if we can build confidence in these results. And so I'll actually start going in that direction by explaining or trying to illustrate what is the autoencoder learning. So the first thing to keep in mind is what is the physical behavior that we expect. And this, I showed you this before, these curves before. This is effectively the main quantity of interest for different angle of attack. What is the lift coefficient generated by different airfoils? And what you're seeing here is the linear regime at low angle of attack, where actually all the airfoils behave in the same way. They have exactly the same lift coefficient. And then things change when you reach the stall, where the effect of the thickness of the airfoil actually is clear here. And so the first question is, are we actually able to distinguish between this linear and nonlinear behavior within the latent space that the autoencoder is recognizing? Again, remember that we're not giving the autoencoder the knowledge of this quantity. We're just giving the flow field to the autoencoder to compress. Well, it turns out if we actually look at what's happening, actually, let me skip this. Let me go directly to this. If we look at the latent space, in this case for an autoencoder with dimension 2, so even smaller than what I was describing before, this is what the latent space looks like. These are the variable V1 and V2, the two latent variables, and this is now colored in terms of the thickness of the airfoil, but also in terms of the angle of attack, in the sense that you see that for low angle of attack, we have actually a linear behavior, a linear correlation between V1 and V2. The latent space is very well sort of ordered, very neatly spaced, and it sort of represents the linear and nonlinear behavior in a relatively straightforward fashion. You see that there are obviously more complexity when the angle of attack increases, but you still see a very clean difference between all the airfoil thickness. So you can easily imagine that you can go back from this latent space to any airfoil, either within these airfoils that we actually included in the database or outside. There is a very clear way to sort of build a broader set of solutions. Now, the thing that again drove my curiosity in this case is, okay, this is an autoencoder with p equal 2, which seems to be reasonable. What happens if p equal 1? If I try to compress it even more? Now, the expectation is that if I compress it even more, it shouldn't work because I do have at least 2 degrees of freedom in the original database that I built, thickness, angle of attack. And so p equal 1 should fail. Well, it turns out it does fail, but fails in a very acceptable and interpretable way. So what happens is that if I only have one latent variable, p equal 1, v1, and I try to compare it to the angle of attack, see what happens in terms of the angle of attack, what I see is that for low angle of attack, effectively, v1 shows a single curve that is linear behavior, and correspondingly, I know that there is no effect of the thickness, and so effectively is able to compress it up to a certain angle of attack. Because it's true that for low angle of attack, the autoencoder should be able to compress those solutions very effectively. As we increase the angle of attack, now the second variable, the second degree of freedom, starts to become important. And in fact, as you can see here, there are multiple values of v1 for the same angle of attack, which means that effectively the autoencoder is failing. It cannot compress the solutions at the angle of attack because there is the need of an additional degree of freedom that I'm not allowing the autoencoder to have. And so this, again, in terms of interpretability, is a perfect example of what is the limit of what you can compress, and you can interpret that limit very effectively. Now, the other case that is interesting is to see what happens in the case where you have unsteady behavior. And again, this is the same curve I was showing you before, the lift. In this case, I'm changing sinusoidally the angle of attack, so there is a cycle that we obtain for the lift coefficient. And this cycle shows some interesting differences between the airfoils that have low thickness, the 0012 and 0014, the thin airfoil, compared to the thick airfoils. The thick airfoils, you see, have a very smooth curve, the red and green, whereas the black and blue have sort of these unsteady behavior, this more complex behavior that has to do with the physics of the problem, which is the presence of a vortex separation at the leading edge for thin airfoils, and the same thing not present for thin airfoils. Well, if we look at latent variables in this case, we sort of see a similar trend in the sense that these are now the plots of v1 with respect to v3 and v1 with respect to v2, so it's a p equal 3 autoencoder. But as you can see, the green and the red actually have relatively simple curves that are shown here. I mean, these are trajectory obviously in three dimensions, whereas the blue and the black have a very, very different behavior for a certain component of the cycle that corresponds to that separation. So once again, the autoencoder is actually representing the physics of these different airfoils differently, simply by trying to compress that information. And this is, again, a sort of an automatic result of the compression strategy rather than something that we're imposing or we are exposing the autoencoder directly. Now, just to conclude this part, this is, again, just to illustrate that is a very effective way of actually reconstructing geometries and reconstructing solution. In this case, the cost of one reconstruction is a fraction of a second on a single GPU compared to many hours of the original calculation. So this is effectively achieving what we want, which is a very fast methodology to compress these solutions. But now, one aspect that I want to point out, which is a little bit different than the classical autoencoders, is the way we actually performing the training. So the process is called, or at least we called it, a sequential training process, where the idea is that we always build a sequence of autoencoder. We start with p equal 1, one-dimensional latent space, and then we increase the size, partly to check the convergence. We want to know what is the minimum size of autoencoders that will give you a good convergence from a loss perspective, but also good accuracy. But the idea that we had was that rather than discarding the information of the smaller autoencoders as we increase the latent space, we actually want to keep that information in the spirit of what we do, for example, with singular value decomposition, which effectively allows us to build formally orthogonal latent spaces, right? Each latent dimension, in that case, singular values, are corresponding to an orthogonal decomposition of the matrix itself. Now, in this case, we cannot do exactly the same because of nonlinearity, but we are actually using the low order latent space to condition the variables in the high order latent spaces, so that there is a sort of a consistency between latent spaces at different dimension. And this, from a practical perspective, helps for a convergence perspective, but also allows us to build sort of an understanding, a hierarchical understanding of what's happening to the latent spaces and to the information that we're adding into the latent spaces. This also allows us to do a comparison, a direct comparison between what we do with SVD and what we do with these autoencoders. So, for example, in this case, I'm showing you what happens if we do SVD versus an autoencoder for the same for a similar data set of airfoils. And this shows again that from a linear perspective, you get a good compression, but the latent space is actually not very well organized. You see actually that some of the red here, or the dark red, actually wrap around the others. These are colored with different airfoils, and so we are expecting that it's difficult to actually interpolate between solution in the linear setting, whereas it's relatively easy to do it in the nonlinear case, in the autoencoder. And more importantly, if we actually look at the ability to compress the solutions, the autoencoder is a very effective in compressing the data set already with a size of 2, p equal 2, whereas the SVD requires a much larger size to get to similar compression quality. And this is actually measured in this case with explained variance, but you can take other metrics and show that effectively the nonlinearity in the autoencoder really fosters this compression, because some of the rank of these data sets is not very low, it's not as low as we would like it to be. So the linear compression are not as effective. Okay, let me switch gear and talk about the uncertainty quantification part, which is the last part that we focused on, which is sort of driving this idea of building confidence. So the first thing I want to say is that we have uncertainty also in physics-based calculations. This uncertainty can be driven by real uncertainty, what I call external uncertainty on the physical inputs. For example, if we don't know the geometry very accurately of the problem of interest. And there is uncertainty due to internal sources. These have to do with, for example, modeling assumptions that we make in this model. And the way we approach the uncertainty in this setting is to actually perform typically an ensemble of simulations. So rather than one simulation, we perform a large number of simulations typically, and by constructing either probability distributions on those simulations, or perhaps more sophisticated construction, we can actually build probability or probabilistic estimation of the quantity of interest, so that we can build confidence intervals. Now, for the autoencoders, we have a similar, or in general machine learning, we have a similar setting where we have external uncertainties exactly in the same way that affect physical inputs, and then we have internal uncertainty, which have to do with modeling assumptions, which in this case, for example, can be the type of architecture we're using, the number of convolutional layers we're using, and so on. But in addition to what we had before, we now have the data. The learning data actually is a major source of uncertainty, because we don't know how much data we need. We don't know, for example, if we cover the entire space of data set that we need to actually make the prediction of interest. And so the question becomes, how can we actually quantify the uncertainty in this setting? And in a very similar way to what we do in physics models, we actually build an ensemble of autoencoders. So what we do is that we typically train many autoencoders that have different architecture and so on the same data sets, and then we try to build probabilistic information of the output. So let me give you a summary of what we actually do. So in this case, we built a data set, again, with very few cases, about 30, but with something very intentional that was built into the data set, which is the idea that we want to do prediction both in an extrapolatory context. So for example, for angle of attack beyond 30 degrees, so we don't have data in that setting, but we also left a gap intentionally in a range of angle of attack to see what happens with sort of an interpolative behavior, but in the absence of data. The type of uncertainty we consider are typically geometry for the external uncertainty, and for the internal uncertainty, everything that has to do with the architecture of the network, the parameters in the network, and the data that we're using. So for example, how much data that we have in the training set as well. And then the basic idea, as I mentioned, is to train an ensemble of autoencoders and then build probability distribution on the outcomes of all these ensemble set. And just to show you directly what the answer is, this is sort of the final, one of the solutions that we obtain. Again, it's reported in terms of the lift coefficient for one of the airfoils. What I'm showing you here is the true prediction, or the ground truth is the red line here. The black line is the mean of the ensemble of the autoencoders, and the blue plot, the blue range, is actually the confidence interval that we obtain. It's also reported here in terms of the size of the confidence interval. So in this case, low confidence interval, so a small size of the confidence interval means high confidence in the results. And what you can see as expected is that we have a large confidence interval, so low confidence in general, in the region of extrapolation beyond 30 degrees. As you can see, the prediction gets lower and lower confidence as we move out, but also similarly a very large confidence interval, so very low confidence in the prediction in these interpolatory regions. That sort of again illustrates how important it is to sort of carefully construct data sets if we want to do predictions with confidence. Now, the advantage of this method is that, in addition to sort of a global metric like this, we can actually also check the importance of each component of the autoencoder that we built. So for example, the effect of adding convolutional layer, the effect of adding or reducing the number of connecting neurons in the connected layers, or the size and the quality of the training sets. Now, in this particular case, the main takeaway is that the effect of the lack of data within the interpolatory region or the extrapolatory region is the dominant one. But there are a lot of other things that you can learn in the situations where instead you have sufficient amount of data. You can see how at a certain level, the amount of data is sufficient and you get better and better confidence in general in the prediction as you increase the number of data. The other thing I wanted to point out is that we have not used a variational autoencoder, because we wanted to effectively build probabilistic information for the latent space directly. And because we built hundreds of autoencoders that have all the same size of the latent space, then we can build, for example, the statistics, in this case, the average and the standard deviation of the latent space variables. And again, this represent, again, the presence of lack of data and clearly identify regions where we can actually go back and improve our data set so that we can improve the confidence of the results. So the idea is that this is a process that can be done repeatedly to get more and more confidence in the results. And so we also perform simulations where we actually introduce an external uncertainty. So for example, the geometry, and we compare the uncertainty induced by that uncertain geometry, either through physics simulation or through these autoencoders. And the results are very consistent. So what we see is that the uncertainty due to the geometry, which is reported in this case with dashed line in terms of confidence, is actually very good. There is very little uncertainty induced by the geometry. And this uncertainty is actually captured correctly both through the autoencoder and through actual simulations, through the simulations, the direct CFD simulations. But this uncertainty is actually much smaller than the uncertainty induced by the architecture of the autoencoder. And so you see the blue curve, which is the total uncertainty. And so this again tells you that in this particular case, the most important source of uncertainty is the data set. and you need to train an autoencoder in a more comprehensive way to get better confidence in the predictions. But you still are able to compare both. So what I showed you is sort of an approach to build a data-driven model with small data set in a principled way, so carefully selecting and proceeding through steps. And this shows that effectively these autoencoders are very effective compressing tools. Again, this is consistent with what is available in the literature. And the difference here is the idea that using deterministic autoencoders, so not variational autoencoders, helps you separating the sources of uncertainty, because you can identify now uncertainty both in the latent variables, so probabilistic representation of those, but also directly separating, for example, the effect of the architecture. And in this case, at least in our setting, in our range, the limited data set is the most critical source of uncertainty. There is a lot of work that is currently ongoing. I'm not going to give you too much detail. I just want to mention that we are working both on three-dimensional geometries, more complex geometry. We are very interested in multifidelity, and there is a very nice extension to this work that we're completing right now that addresses multifidelity. And then effectively the real-time computing for doing maneuvers is what is our ultimate goals. Maybe the one thing I'm going to share with you is how we are doing the multifidelity, which is perhaps the most interesting part. So the basic idea of the multifidelity is that rather than taking advantage of low fidelity data set to add to the solutions can be effectively very useful. And the way we are doing it is through the same concept of sequential training. So what we are doing is that we are training the first autoencoder with, for example, non-viscous solution, Euler solution of this problem. And this gives us an autoencoder that effectively can reproduce those solutions. And then we are adding additional data, and for example, runs data, viscous calculations, and we are increasing corresponding the latent space, but by conditioning so that we are still representing the effect of the Euler solution directly in the case. And what we see is that for low angle of attack, so in the regions where we don't expect a lot of inaccuracy given by the Euler solution, we actually have the fact that the latent space is actually consistent in the two cases, but the added variables effectively are representing the viscosity, the effect of viscosity. And so the idea is that we can separate very neatly, very clearly the effects of low fidelity versus high fidelity directly by conditioning the latent space. And this is work in progress, but I think it's very promising, especially for complex application where building databases of high fidelity can be quite daunting and quite complex. Okay, I'll stop here. I have some references here, but again, I'm happy to answer questions and also connect afterwards if you have more information. And I do want to acknowledge Ettore Saetta, who was a PhD student at the University of Naples that spent some time with me here on campus at Stanford and continues to work on this topic and both the architecture and the application in aerodynamics. Okay, I'll stop here. So thank you for your attention, and I'm happy to take questions.
Thank you. Thank you so much for the wonderful, wonderful talk, Gianluca. That was awesome. We already have two questions in the chat box. I can.
No, I just opened it. I can see it. Do you want me to start from there?
Okay, yeah. So start from the first question from Maya. Yeah.
Okay, how does the method handles noise in the input training or testing data? Perhaps do. Okay, that's a great question. Now, I should have said this before. We are targeting numerical simulations for this, so we haven't effectively studied the effect of imperfect measurements because, again, we're hoping that this is a method to compress simulations, at least the way we designed it. But one thing that we did, which is very interesting, is that when we started the project, we started to work because it's a convolutional network with images in our inputs, and images by virtue of going, translating between, say, a CFD solution to, for example, RGB maps, and going through contour levels introduced actually noise. It's very specific noise. It's not, random noise, but it is truncation and it is an approximation. It turns out that we noticed that the latent spaces are actually quite affected by simply having, for example, a conversion to RGB or a conversion into contours rather than raw values of the inputs. And so what we found is that, and this is probably what you'll see when you have noise. So what happens is that the latent space representations are not as clean as the one that we have if you have noise. And so it might be more difficult to interpret it, especially in the absence of enormous amount of data. So that has been our experience, at least. And I imagine, I haven't done it with actual Gaussian noise or real noise, but I think the effect will be the same. So the noise in the input will be directly represented in the latent space in terms of cleanness. And this is part of the reason why variational autoencoders tend to be popular in that setting, because you sort of account immediately for that noise. As I said, we wanted to be very clean in terms of the inputs that we generated. Okay, how does the computational cost, hopefully I answered the question. How does the computational cost of the autoencoder compare to that of a RANS fluid simulation of flow flow? Yeah, I maybe flashed this too quickly. So for steady calculation, unsteady calculation, the ratio of cost is many order of magnitude, as one would expect. This actually increases even more. These are two-dimensional cases. As you go to three-dimensional cases and perhaps try to capture even more sort of detailed solutions, the expectation is that more and more the factor, the multiplier will be large. Obviously, on the other end, if you're doing two-dimensional steady, perhaps coarse simulations in RANS, the differential is not that large. But in our examples, it's still multiple order of magnitude. And this is the cost of evaluation. Obviously, there is the training cost, which is added to that. But if you're talking just about evaluation for a new case, obviously the multiplier is many order of magnitude.
I think the Mark is asking about the training cost.
Okay, the training cost. So the training cost, again, our strategy has been to use very small data sets. So we're talking about less than 100 data sets. And so the cost is never larger than few hours typically on single GPUs. We did not really have to go much higher. Now we expect, again, as the database increases, not in terms of number of cases, but in terms of details, because now we're using perhaps three-dimensional data set and so on. We are obviously seeing much larger cost, but still on single GPU, we're still talking about order of hours, no more than that.
Thank you.
Okay, so how can you predict two different values for the same angle of attack for noise up and down motion from the snapshot training? I see. That's a good question. So what we do is that we use batches, and the batches actually include 3 cases. So we typically have it's sort of implicitly we are giving a time variation in the setting that gives a difference between, say, nose up and nose down. So we're not formally giving the dynamics, the full dynamics, but we are capturing sort of instantaneously, if you like, a DDT, a change in time of the actual solution. So that has been one idea that obviously we were trying to pursue is to build dynamic models in the latent space. But rather than providing full information about trajectory, we wanted to just give sort of bursts, just very short time duration for the batches, and that seems to be, at least for this case, is sufficient. Now I can anticipate that I should mention this. In this problem there is an extra degree of freedom, which is the frequency in time. So what's called the reduced frequency, right? It's not only a range of angle of attack, it's how quickly you're going to those angle of attack. So everything that we've done here is fixing that frequency so that we don't have an additional degree of freedom. But if you do have that additional degree of freedom, our expectation is that you need to provide more information. You need to provide some sort of rate of change of angle of attack with time to be able to actually do the prediction. In this case, that was fixed, and so we sort of assumed that that was sort of known. Hopefully that answers your question. Oh wow, there are a lot of questions. Okay, I lost track. Where am I?
Joe, next question is by Joe.
Oh, okay. Just learning about, but from what I've seen, variational autoencoder are more ideal for generation. Does a basic autoencoder well here due to the more narrow system? Yes, absolutely. So the basic idea here is that we have a very clean data set, so we don't have noise, and so in this way, the variational autoencoder does not really provide a lot of advantages in this case. I think that is important that we didn't want to assume a probabilistic description, say Gaussian model or mixture of Gaussians and so on in the latent space, because we wanted to inform that through our ensemble of autoencoders. So our idea is that the probabilistic information in the latent space come from the combination of all these ensemble of all these autoencoders in the ensemble, rather than through an ansatz on the probabilistic model for the latent variables. Hopefully that answers the question.
Mm-hmm. Next one is by Khalid.
Can you please explain a little about sequential training for the multifidelity problem? Do we train the low fidelity data with low data and increase the problem comparison to? Yes, exactly. So what we do is that we train by using the low fidelity. In this case, low fidelity means inviscid, non-viscosity. High fidelity means with viscosity, but you can imagine a different setting. But the basic idea is that we train first on the low fidelity. And then what we do is that we add to these low fidelity cases the high fidelity. So we have for each, we have the two data sets sort of combined together, okay? And then what we do is that we condition the first variables in the latent space using the previous results, and we build basically a representation of the full data set. Now, the key here is that we tried both by making each case. So each time we have an high fidelity case, the question is if we need to have a low fidelity corresponding or not. And it turns actually for, at least for this problem, that was not that critical. Even if we don't have a corresponding low fidelity, the two latent spaces, can be combined in a very clean way without too much trouble. But I expect in some other situation, you will need to be able to differentiate between low fidelity and high fidelity and discard the low fidelity cases whenever you have an high fidelity, so that you neatly sort of distinguish the two kind of information. At least for the examples I gave you, that was not necessary. But as I said, that's work in progress. So we'll see a little bit more as we expand the scope of some of those analyses. And you're right. I think the challenge is how complex is the physics that you're adding, or another way to say it is how good the low fidelity modeling that you're using is. Because if the low fidelity modeling is very inaccurate and very unable to reproduce some of the features, then it's very likely that the conditioning is really not very helpful, because you are not able to use much of the information from the low fidelity. So I think the challenge there is to understand, from looking at the latent space, especially in the low fidelity and in the mixed space, sort of the combined space, if that information is actually interpretable. That will give you a set of at least some confidence in the outcomes, right? If there is no real connection between the two, then likely what this means is that your low fidelity model is not a very good representation, very useful representation for the combined or for the physical problem. Okay, let's see, where am I? Chris.
Next is Chris, yes.
With your method of multifidelity for noisy experimental data, for instance, could you add a new latent parameter, but have it to be a variational latent parameter and keep the real? Oh, that's an interesting idea. There is no reason not to. In fact, one of the things you can do is that you can actually build a variational autoencoder, but where you condition for the first variables, you condition the variance to be 0. And so naturally it will be sort of variational only for the final set of variables, right? So the same ideas, you can definitely use it. We haven't tried it. I don't know if it will be easy or not, but at least conceptually, yes, you can definitely do that. And it would be actually very interesting to try. Because as you say, there are some additional, now what I said before, we don't want to use, variational autoencoder because our data set is clean. Now, obviously, in multi-fidelity, that's not the case anymore, right? The data set is not really clean because the low fidelity cases have errors with respect to the high fidelity cases that are not really captured in the inputs. And so the variational, the additional, the variational, the variance in the latent space might actually help with that. So it's a really good idea. In fact, maybe we should talk more about that afterwards if you're interested.
So I copied Wesley's questions.
Oh, okay. The plots show are CLCD polars. If the integrated quality is the goal, would the training benefit or worsen from this error? Oh, great question. Yeah, the reason I would, let's say, I don't know. We tried originally to build autoencoders with only the integrated quantities in mind. And yeah, as you can imagine, it's relatively easy to do that. But what we wanted to do here instead is to reconstruct the flow fields. And we are extracting the lift and drag from the flow fields, from the actual pressure that is reconstructed. So this is effectively a harder problem because we are not, constraining the pressure distribution on the airfoil or the integrated quantities. But the reason why we want to do this is because, again, remember, this is a process of compression of those flow fields. So we don't know exactly how these flow fields are going to be used. And so we don't want to limit ourselves to just the aerodynamic coefficients. We just want to reconstruct typically the velocity fields. And so for us, the goal was to reconstruct the fields. We're just using the lift and the drag as a way to summarize it. What difference does the training process have for 3D unsteady turbulent flow? So at least in our project, what we're doing, three-dimensionality doesn't change anything. Obviously, the complexity of the geometry, the size of the data set, that's fair. But there is nothing that changes. Unsteady per se is not a problem. As I mentioned, as long as these are reasonably well described flow field in terms of times and data sets in terms of times, I think we can handle it. Turbulence is a different story in the sense that if you're interested in the time varying behavior of a turbulent flow, so the instantaneous, I would argue that probably the amount of data required is way more than what we're thinking here. So what we are doing here is to try to represent the statistics of a turbulent flow. So say a time average solution of a turbulent flow. And in that sense, I think the solutions are expected to be smooth, changing smoothly on a large time scale. And so we're expecting that to be possible even in a more complex turbulent flow, say computed through a large eddy simulation, for example. But we're not, at least at this point, these methods are not targeting the instantaneous variation of a turbulent flow. That would be, at least in terms of complexity and size, really beyond sort of the scope of what we're trying to do. And there are obviously, both in the labs and around, there are a lot of efforts in that direction. And you will see easily that, going to these low dimensional latent spaces is really not practical for those cases. The dynamics, we know the dynamics in a turbulent flow are much, much higher dimension than 2 and 3. So the whole scope of the problem will change.
Okay, well, I think that was it from the chat room. But is there any question from audience who wants to unmute yourself and then ask questions? If there are, please do so. Well, I guess we don't have audience with a question who wants to unmute. Well, thank you so much for the wonderful presentations and Q&A session. It was awesome and very smooth.
Well, thank you very much. Appreciate it. And thank you again for the invitation and for the attention. Thanks.
That's awesome. Jian, would you mind sharing the slide with me?
Sure. No problem. I'll send it to you.
Okay, awesome. Well, thank you for the one.